DeMoive's Theorem. Hope I've pronounced that correctly. Pardon to those that can actually speak French. Our objective here, we want to apply DeMoive's Theorem to raise a complex number to a power. Now we know that when we have an exponent or a power, it's just repeated multiplication. So if we had a complex number raised to a power, we could just solve it by multiplying and then multiplying again and then multiplying it again. But that can get tedious if the power is, say, above 3, all that multiplication. So we're going to talk about a theorem that allows us to do it in one step. Let's recall a couple of things we already know. We already know what the exponential form of a complex number looks like. It's r times e, the natural number, raised to j theta. J is our imaginary unit, and theta in the exponential form is in radians. And we're just using it here to come up with the formula. And we have two laws of exponents that we're going to apply kind of at the same time. A times b, the product raised to an exponent, is equal to the individual factors raised to the exponents and then multiplied. And a to the m raised to the n is equal to a raised to the product of m and n. Okay? So we're not going to get too much into where all this comes from. We just want to make use of this theorem to raise a complex number to a power. Use the exponential form of the number and apply the applicable laws of exponents. Okay, so here is the exponential form of the number, r, right up here, times e to the j theta, and we're going to raise it to a number. I'll call that number n, and then we're just going to apply the two laws of exponents. This results in r to the n times e to the j n theta. So there you have it, okay? So this is what we're after here. Let's extend this to its polar and trigonometric form, and we're also going to extend it to we're going to show it in the shorthand version. And again, I'm not going to get into how all this works. I'm just going to write it down, then we're going to apply it. Okay, so in the polar trigonometric form, it is this. So we're going to take the polar form, the polar or trig form, the long form, r times the cosine of theta plus j times the sine of theta. And we want to raise that to the nth power. And what you're going to do here is we're going to take this part again, we're here, so we're going to raise r to the nth power, similar to right up here. And then in this case, in the polar trigonometric form, what happens is we have the cosine of n times theta, I'll put those in parentheses to make that a bit clearer, plus j times the sine of n times theta. And again, I'm not showing the proof behind this. This is, if we extend all of this and get it to its polar form, this is what comes out. In shorthand, r with this angle symbol, theta to the n, well, it's the same idea. The r gets raised to the n, and we have the theta being multiplied by n like that. Okay, so let's note a couple things. The magnitude is being raised to the power. Okay, the angle is being multiplied by the power. Here's the magnitude being raised to the power, and here is the angle being multiplied by the power. Let's do two examples, and see it in action here. Let me get myself set up for you. Okay, example number 1. Let's use DeMoive's theorem to find 2 plus 3j raised to the third power. Again, we could rewrite this extended, 2 plus 3j times 2 plus 3j times 2 plus 3j, and we can multiply the first two, get an answer, and then multiply that answer times the third one. That can get a little tedious, and if this power were 5, it would be 5 multiplications. So let's use the theorem. Okay, so first things first, because our formula is in polar form or trigonometric form, let's rewrite this in polar form. So let's convert 2 plus 3j to polar form. Okay, and so our r is equal to the square root of 2 squared plus 3 squared. This is going to be equal to the square root of 13, which is approximately, I'll go to the 100th, 3.61. We know that from past work we've done. Notice that we are in quadrant 1. We noticed here a positive real and a positive imaginary. So we're in quadrant 1, which tells us that our reference angle is equal to our standard position angle, which is simply the inverse tangent. And we can use absolute value symbols, the absolute value or the parentheses, because we're in quadrant 1, it doesn't matter. The vertical divided by the horizontal. And this I will also round to the 100th. So I'll do this as an approximation, but we're going to use this number. And I've done it in degrees, 56.1 degrees. Remember, the polar and trigonometric form can be in radians or degrees. So we have our r and our theta. Okay, so we know that 2 plus 3j is equal to r, 3.61, times the cosine of 56.31 degrees. Whoops, making a mistake here. 56.31 degrees plus j times the sine of 56. Boy, I'm having a tough time writing my numbers correctly at the moment. 56.31 degrees. There we have it. So now we have it in polar form. We can do the exponent. We can do the power using that formula. So this means that 2 plus 3j cubed is equal to this cubed. Okay, so I'm gonna write it out. This is 3.61 times the cosine of 56.31 degrees plus j times the sine of 56.31 degrees. So I just cube this, and oops, I got a cube. Sorry about that, a little bit short. Let's see, I got to close that one and then close that one, cubed. And what do we know? Well, we're going to cube. We raise the r to the power, and we multiply the angle by the power. So this equals 3.61 cubed, okay, times the cosine of 3 times 56.31 degrees plus j sine of 3 times 56.31 degrees, okay? So again, the exponent 3, the r is raised to the power, the theta is multiplied by the power, and I'll do that with a calculator and round these to the 100th. 3.61 cubed is 47.05 times the cosine. 3 times 56.31 is 168.93 degrees plus j times the sine of the same answer, the same angle, 168.93 degrees. And there you have it. And of course, we can go back to this if we need to, by simply multiplying through by this 4705 here, which we're going to do similar in just a second. So there you have it, DeMoive's theorem to go from the standard rectangular form raised to this exponent right here. Let's do a second example. Let me get my stuff out of the way. Hopefully nothing falls on the table. Okay, but I'm going to give it to you, and this time we're computing 3 times the cosine of 120 degrees plus j times the sine of 120 degrees raised to the 4th power. And we want to write our result in standard form. Okay, so what do we know? Well, we're already in. We can already write this using We can already use the exponent because we already have it in polar or trigonometric form. So we're going to raise the r to the exponent, and we're going to multiply the exponent times the angle. So let's see here. I'm going to rewrite it. 3 times the cosine of 120 degrees plus j times the sine of 120 degrees, all of that raised to the 4th power, is going to be 3 to the 4th power. Again, the r is raised to the power, and then we're going to multiply the angle by the power. So times the cosine of 120 degrees. Whoops, I'll write the 4 first. I did that last time that way. Cosine of 4 times the angle, and again I'm in degrees, plus j times the sine of 4 times the angle. There we go. Okay, now we can put this together. 3 to the 4th, we can do the math. 3 to the 4th is 81. 4 times 140 is 480 degrees. And let's remember that this is greater than 360, so let's back off by 360 to get an angle that's between 0 and 360. So let's note here, 480 degrees is greater than 360 degrees. So let's unspin it a little bit. Let's back it off by 360. And we notice that the angle between 0 and 360 turns out to be exactly the same as we started with. So we're back to here, so we can rewrite this the same form as 81 times the cosine of 120 degrees plus j times the sine of 120 degrees. Obviously, that's just getting a bit lucky. That 120 times 4 got us around the circle exactly 1 time. Here's our answer, but we want this to be in standard form. So let's just simply do our distribution. 81 times the cosine of 120 degrees turns out to be approximately to the 100th, 40 to the 10th. I think it's 50 actually, to the 100th, and then 81 times the sine of 120 is going to be 70.15 again to the 100th times j. So there we have this one, already in the form that our formula helps us with. So we just need to do the math, and then they wanted it in standard form. So once we came to the answer, we just distributed the 81 to come up with our answer in standard or rectangular form.